Hi ladies and gentlemen, I just wanted to have a couple of short videos here that address logarithms and trigonometric functions. I want to provide some basic insight into these things since a lot of people identified them as issues associated with their assessment for the pre-calculus portion. So here's the video on logarithms. It's really straightforward. You just have to remember the one thing about logarithms, which I've written here. Logarithms are exponents. I'll get into the history of them when we, if you want, but what I want to talk about right now is this very important fact and how it makes logarithms straightforward to think about. You still have to practice, of course, but let's think about what logarithms are under the understanding that logarithms are exponents. Let me write down our first problem. So log base 10 of 1,000. What are logarithms? Logarithms are exponents. We are wondering what is the exponent that goes with the base number 10 that will give us 1,000. Well, we can rewrite this. This is the same, of course, as log of base 10 of 10 cubed. And then we can see very clearly that the exponent here is 3. That's all logarithms are. Because of this, we know log base 10 of 10 is equal to 1. That seems very straightforward, and it's fundamentally one of the most important things that we do. Another really straightforward thing is log base 10 of 1. What's the exponent that I need to put on a base of 10 to come up with 1? That exponent is equal to 0. Logarithms are exponents. Let me write down another problem to help expand this idea. All right, here we have the log base 10 of 1,000 squared. Well, since we're doing base 10, we really need to think about this in terms of 10 raised to some power, because the logarithm's the exponent. So this is equal to log of base 10 of 10 cubed quantity squared. So you can remember your rules for exponents. The rules for exponents and the rules for logarithms are the exact same. They're just reversed because logarithms are the inverse functions for exponents. So in this case, if I want to rewrite this, this would be log 10 to the 6th power. So the exponent, and this is log base 10, is equal to 6. Another way that we can attack this one is using one of the log identities that perhaps you're familiar with. The point is, because logs are exponents, it's really just the exponent rule that you've learned previously. So what I'm going to do is I'm going to pull the 2 outside because the 2 is an exponent. And when I have exponents inside of parentheses, what do I do with them? I multiply them. And because logarithms are exponents, we're going to multiply. So we have 2 times log base 10 of 10 cubed, which is equal to, that's 2 times 3, which is equal to 6. So this is one of the very important rules of logarithms. If I have something inside the argument, right, so something that is inside here, and I have it raised to a particular power, because I'm going to multiply those exponents, I can actually pull that number out front of the logarithm and just multiply on the outside because logarithms are exponents. Let's look at another problem. In this situation, we're going to look at log base 10 of 100,000. Now, of course, we could do this directly. This is just log base 10 of 10 to the 5th, which we know is equal to 5. I want to do it in a little bit different fashion to demonstrate another property of logarithms, which is the same as the property for exponents. So consider this. Log 10 of 100 times 1,000, and that's of course equal to log base 10 of 10 squared times 10 cubed. So what do we do? What is the rule for exponents when we multiply numbers together with the same base? We add the exponents. Well, that, of course, because logarithms are exponents, are exactly what we're going to do here. This item becomes log base 10 of 10 squared plus log base 10 of, I've run out of room here, of 10 cubed, because logarithms are exponents. So what this is equal to 2 plus 3, which is 5. Everything we're doing with logarithms supports the one idea of what logarithms are. Once you become comfortable with that, once you practice, then it's really straightforward to see what logarithms are. And I'll talk in just a minute about what we use them for. One more example problem to demonstrate one of the final important properties of logarithms. All right, in this situation I have log base 10 of 1 over 100. So of course you know this is log base 10 of 100 to the negative 1 power. But as we saw above, when we have an exponent up here, we can just pull that out in front. So this is equal to log base 10 of negative 1 times 100, which is equal to, and the exponent for base 10 of 100 is 2. So this is equal to negative 2. This is where the whole rule comes about, hey, if it's in the denominator, then you're going to have a negative out in front. Okay, no need to memorize any of that stuff. It's very straightforward. It's just the exponent. It's the exact same thing we would do with the exponent. Let me give you one final example. All right, let's talk about log base 10 of 37,000. So this is equal to log base 10 of 37 times 10 cubed. Well, we already know from the rule of exponents that if we're multiplying things, we're going to add the exponents. So we're going to take what's on the inside here and we're going to have the logs added together. So this is equal to log base 10 of 37 plus log base 10 of 10 cubed. And we know log base 10 of 10 cubed, this is 3. So what we're left to do is figure out, what is this thing here? This is the exponent that goes on 10 that's going to give us 37. So it's really, hey, what is the logarithm's the exponent? What is that exponent that's going to give me 37 given that the base is 10? Well, we know because we're between 10 and 100, 37's in here somewhere, that exponent's between 1 and 2. This is where there were ancient techniques, ancient being a few hundred years ago, where they would go through and calculate logarithms. Those still exist, of course, but there's no need for us to do that. We have calculators. And so we can quickly calculate what this is. Let me write that value down. That value is 1.5, approximately 682. So this value here for the question mark, that exponent, is about 1.5682. So I substitute that back in for my log base 10 of 37, and what I find out is log base 10 of 37,000 is the sum of these two things, which is approximately 4.5682. One more time, what is it that we found? What is this number? This is the exponent, that if we put it 10 to that exponent, then we're going to end up calculating 37,000, approximately. This is what logarithms are. You want to practice with the rules, but I want you to always be comfortable with the idea of what logarithms are. If you want to hang on, I'll give you a little bit more of the history with John Napier and why he invented the logarithms in the first place, as well as kind of the modern application of what we use them for. Because, of course, what John Napier invented logarithms for is no longer relevant because we have calculators, computers, things that will do computation for us. Hang on if you want to see that. So, logarithms were invented by John Napier back in the 1500s. He invented them because, of course, there were no calculators and computers, and they needed to be able to solve problems. Of course, they lived in a completely different world in many ways, of course. But with respect to how they worked with mathematics, they did natural science, all of the aspects of what humans were learning at the time. The reason that Napier came up with logarithms was to address problems like this one here. So let's say we want to take the product of these two numbers. To go through the hand computation of grinding out this product is quite labor intensive. And of course, it doesn't matter where we slide the decimal points. This could be 5.712 times 6.842. It's the same type of problem. There is a lot of work that goes into doing this. So what Napier is doing with logarithms is simply leveraging the fact that when I'm multiplying numbers together, I am adding their exponents. And it's much easier to add things together than it is to multiply things together. So that's how he built this entire concept. Let me give you the demonstration. So this problem, what I've done is just change the numbers into their base 10 representations. 10 raised to the 3.756788 is approximately equal to 5,712. And similarly with 68,420, I have the number here. Notice we know that there's going to be the 3 point, etc., etc., and the 4 point, etc., etc., because of where the decimal place is in these numbers. So we know where the decimal is, we know what that piece is. So the logarithm tables actually only needed to be developed for numbers between 0, not including 0 of course, and 10. Because once you got up to 10, then you had 1. So what he did was he said, hey, instead of multiplying these things, what I'm going to do is I'm going to add together the exponents. I realize that whatever this thing is, it's equal to 10 raised to the 8.591971 power. So if I had a table that allowed me to convert this number into its exponent, the 3.75, etc., etc., and this number into its exponent, then I could just add the exponents together and use the table to go backwards. And that's exactly what logarithmic tables were. So before we had calculators, this is how we were able to do large multiplication problems. The slide rules that perhaps your grandparents or parents talk about when they were doing mathematics, it's all based upon this idea of logarithms. They did multiplication by adding exponents together. So then we reverse this back out, and this number comes out to be 390814798. Right? So that's 390,814,798. That's not exact. It's an approximation. Again, back in Napier's day, they had to approximate everything. And we do basically the same thing now, but our approximations are more accurate. So the actual number, if you were to multiply these together, is 390,815,040. So that gives you an idea of where the error is with these things. So why do we do logarithms nowadays? Of course, there's some modeling issues. There's always the fundamental concept of what logarithms are. Logarithms are exponents. And because of that, we have lots of ways that we can make use of them. The primary use that we have for solving problems in the modern era is for problems that look like this. So when we have a problem that looks like this, where the unknown, in this case, is x, and that unknown appears in the exponent, then we use logarithms. Because logarithms allow us to get at the information because logarithms are exponents. So what we would do in this case is we would divide both sides by 237, and we would have e to the x is equal to, and we'd have 49,812 divided by 237, which we could easily do the calculation on. But then what we would do is take the natural log of both sides. So here we take the natural log of e to the x and the natural log of 49,812 divided by 237. And then, of course, the natural log of e to the x, that's x times natural log of e, and that's equal to 1. And then that would be equal to whatever this number is. Natural log, I'm not going to write it out again, whatever it is. And that's the answer. So the natural log allows us to solve problems where the unknowns are up in the exponent. Hope you've enjoyed this little bit of review on what logarithms are. If you keep in mind as you're practicing, all they are exponents. Logarithms are exponents. You keep that in mind, help you learn the material very quickly. Thanks very much.